Good morning to everyone. And that was the Reverend Al Green. And what cut was that? John, do you know? Okay, Reverend Al Green in a cut from his album. So we'll let that go there. This is our last week of the semester before we go into finals. And so a lot of what we're going to do today involves finishing up Chapter 9, talking a little bit about the schedule, and answering questions, but essentially we're in Chapter 9 at this point, and that's where I'm going to spend my time for today and tomorrow. And on Wednesday, probably look a little bit of an overview depending on how many questions are on graphing, but this is going to be a big week for graphing. And then, of course, the final itself. So as we look at the document cam for a moment, if we could, John. This is the week 15 of April 20th, and it's chapters section 9.2 and 9.3. I'm going to be looking at 9.2 and 9.3 both today, and a final review. So as we come off there, and let me go ahead, and we're going to come back here in a moment to the document cam, but a comment for you in terms of what we did in Math 10. The material in Math 10 was based on the simple closed curve. We looked at graphing. We talked about René Descartes in the 1600s. 1637, he actually publishes a book called The Method, and there's a note in your text that we have this semester talking about that. And the idea of graphing was very critical to the development of mathematics that took place in the 1600s. You have René Descartes in 1637 with the publication of what we call now analytic geometry, and then the idea of graphing, and you have Newton just 30 years later, 32 years later, developing the calculus, and then the rest just took off from there. But we refer to this coordinate system as the rectangular coordinate system or the Cartesian coordinate system. So the Latin for Descartes was Cartesius, and therefore it became known as the Cartesian coordinate system, and that's, of course, the alternate to the rectangular coordinate system as we go to the document cam. And we have there the rectangular coordinate system, and when we talk about an ordered pair, and we have two number lines meeting at right angles. I'm going to go down to the way it was initially presented to us by Descartes. But we talk about the origin, and that's the usual thing we saw in the Math 10, nothing particularly new to that. But when I ask you to do a coordinate system, I expect you to draw a horizontal, vertical line and label it. And I've mentioned to you that this is one of the very difficult things for students in algebra. They seem to learn it one semester, go to the next semester, relearn it, go to another semester, relearn it, 4 times of relearning it, and still not where I'd like it to be on any particular class, whether it's an algebra class, a stat class, pre-calculus. This is one of the most important things you can learn out of 10 and 20. So again, get a straight edge. You will not be given graph paper. You will be expected to draw a coordinate system and plot points. Okay, so the idea of plotting a point, which is sometimes referred to as the ordered pair, but if I just look at, and this is very similar to the quiz you had in this unit as we go to the document cam, where I gave you a letter and asked you to give me the ordered pair with it. You may recall the test questions you had in something like this. The ordered pair for A is 2, 3. So you think of starting with the origin, going over 2, up 3. So I always think of starting with the origin, going to the left or the right, and then you go up or down. Now, as we come off there, the comment for you is for every point in this, what we call the Cartesian plane. So this coordinate system we set up is called a Cartesian plane. For every point that's there is an ordered pair, and for every ordered pair, there's a point. That is a critical aspect of what we think of in using the Cartesian plane to plot points. Now here is the showing the coordinates. We talked about this as we go to the document cam. These were the coordinates, I should say quadrants with the coordinates. So remember if the ordered pair was plus plus, it was in the first quadrant. And remember this goes counterclockwise. So as I'm tracing this circle going counterclockwise, then first, second, third, fourth. Now that doesn't become too important, okay, until we coming off there now, John. Not too important until you get into like trigonometry. And when you start talking about certain ordered pairs related to the right triangles. So we talk about tangent functions, sines, cosines, and we need to know something about quadrants there. And that's well beyond where we are, but it's just a point that you need to be aware of. The one new thing that we see on page 665 that you haven't done before is looking at what we would call, as we go to the document cam now, the midpoint of the line segment joining 2 points. So I'm going to leave that on the screen for a moment, and I'm going to go to the board in a moment here. Let's leave that on the screen. And I'm going to draw a coordinate system, and I'm going to give 2 points. Okay, we can go to the board now. So I have, at this point, let's bring that in tighter if you would, please. I want just about that much there, John. Much tighter. Bring it in tighter. There we go. Now, at this point, we have an x and we have a y. That's my vertical and horizontal axis. And these are supposed to meet at 90 degrees. And a usual idea that's in graphing is to use the letter P for a point. So I'm talking about point 1. And the ordered pair for that, x sub 1, y sub 1. So this may be my point P1. Now the point on the left is called P1, and a point to the right of that will be called P sub 2. So I might have a point over here called P sub 2, and I'm going to talk about then x sub 2, y sub 2. Very typical notation. And so the idea is I can join these 2 points. And I probably should give a little more space there for what I need to do. So I'll just call this P sub 1 below. And I'm going to join these 2 points. And of course, one of the big issues out of geometry, as stated by Euclid, is that 2 points determine a unique line. There's only one line that can be drawn through those 2 points. And this is a line segment because I've stopped it at the endpoints. Now this creates a right triangle in the sense that if I come over here and draw a right triangle, then the argument is that I would like to find a point that's halfway between P1 and P2, called the midpoint. Now, the formula for that, as we go back to the book, the document cam, notice it's arguing that we add, or we average, if you will, the 2 x's and the 2 y's. So the midpoint is going to be given by x sub 1 plus x sub 2 over 2, y sub 1 plus y sub 2 over 2. Now I drew the triangle in for a reason, and I'll just move over here. This is your ordered pair for the midpoint. Now again, I'd prefer that as a shot if we could, John, because I want nice and large on the screen. So this works real well, and I'll just work around it. Now, the midpoint. We talked about similar triangles, right? Okay, so what I'm just going to do is come back up to this diagram, and I'm going to think of drawing a vertical line here through that midpoint. Now, I didn't get that as vertical, looking vertical. I should have something more like that. So let's see if I can clean that up. Now, this smaller triangle is similar to the larger triangle. because they have the same three angles. Remember, this is like a right angle here, a right angle here. They share this common angle, and so you could argue, since all three angles have to come up to 180, or these two acute angles have to be complementary, since this is a shared angle, this angle must be the same as this angle, and that's the way we sometimes show it. But my point here is, if this represents the midpoint between here, then by proportions, we could set up a proportional argument that this shorter part is to the whole as this short part is to the whole. They must be in the same ratio, hence 1/2. So that's why we take this distance between x1 and x2, add those two together, and in essence get the midpoint of this line segment that is the base of the triangle. And we can argue exactly the same way. If I run this triangle, then this upper triangle is similar to the lower triangle, and we can go through the same argument. So we have a midpoint for any line segment joining 2 points that are given to us. So again, that formula right here, just want you to be aware of this formula. So if I ask you to find the midpoint of something, that's critical. Now, I'm going to do something else. I'm going to rewrite this triangle, and so what we're going to do, John, is just pan over just a little bit to the right. I'm going to just replicate that triangle, or a rough approximation of it. Trying to run that parallel coming over there. And so this should look like the other one. And I'm going to, in the process, consider this side now as a distance. Now, I'm going to call this x sub 2 minus x sub 1. Now, if you think about where this point is here, this is x sub 2 here, y sub 1, that is where the right angle is. But the distance from the vertical is just x2 minus the x1. And in the same way, this leg is y sub 2 minus y sub 1. And I'm going to, for the moment, call that little d for diagonal, also for distance. Now, what I want to contrast for you is this midpoint formula right here, and another formula I'm going to create using the Pythagorean theorem. And I'm just, for the sake of argument here, I'm going to give you 3 formulas today, because these 3 formulas you need to see at this level, and then it's something we really hassle or fight for the next umpteen semesters that you take mathematics. But what I'm going to say is, by the Pythagorean theorem, the diagonal squared is the sum of x2 minus x1 squared plus y sub 2 minus y sub 1 squared. That's just using the Pythagorean theorem. And let's just tweak that just ever so slightly to pick up the square right there. A little bit more. Now, I can take the square root of both sides, and we get a new formula called the distance formula. And so it is x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Inside the radical, I take that and get a distance. I'm going to illustrate that by taking, for the moment, and are you in camera 1 or 2 at this point, John? 2? Okay. Could you bring camera 1 in about just exactly where you have camera 2 for the moment, because I would like to come back to that. No. Okay. I was hoping you would do that before you made the switch. Okay, yeah, and bring camera 1 so we have the same shot, and then make the switch as we go to camera 2 over on the right. So if you'll bring that for camera 1, and then we'll free up camera 2. And then I'll need some space to do what else I'd like. Okay, now we're going to take camera 2 and bring it over here so we don't have to do a pan, and I can come back and forth. So let's say I have 2 points, and I'm just going to indicate these 2 points here now. And let's say that this first one is, and looking at about where things are, it looks like maybe a 4, 5 is the point I want there. And at this time, let's call this one, and I'm thinking that looks like it might be up another 2, so maybe at 6. And let's say that that is up to, say, 8. I'm just going to take those as possibilities. Now let's see how that's going to go. Now what I'd like to do is bring this in a little bit tighter here if you could, John. And what I'd like to do, and over to the right so I have some space, I'm going to use the formula we just said, and I'm going to call this P1 and this P2. Now note, I'm supposed to take the y2's and the x2's. So I'm going to take x2 minus x1. Now this is x sub 2, y sub 2. This was x sub 1, y sub 1. So I take x sub 2 minus x sub 1. That's 6 minus 4. And square it. Then, I don't like what I did with the squaring there, so let me clean that up. Make that 2 more readable. And then I have 8 minus 5. And square that. Now, with what I have there, as we just look at it, and I'm going to now carry this through as d, and so that's the square root of 2 squared. So I have 2 squared, which is 4, and then 8 minus 5 is 3, and 3 squared is 9, and so that's going to be the square root of 13. And that's how we find the distance between 2 points. So this is the distance between P1 and P2 for a particular ordered pair. Okay. A distance formula. Now the midpoint between those two, a little different. Let's look at the midpoint now. So we'll slide over and left justify there. So my midpoint now is going to be where I go ahead and I'm going to run that now as, let's see, I want x1 plus x2, so that's 4 plus 6 over 2. And then y1 plus y2 over 2, that's 5 plus 8 over 2. And so the midpoint of the line segment joining P1 and P2 is going to be 10 over 2, which is a 5. And then I have 5 and 8, which is 13. So I'll have 13 halves. So that is the midpoint. Now one more comment for you. One more formula. And this, the importance to distinguish between midpoint and distance. And now I'm going to talk about the slope of the line joining these 2 points. So I'm going to look at slope now. The slope of the line, and that's how steep it is. If you've ever been on ski slopes, you know what it is, have a steep slope or a bunny slope. And the pitch of a roof is in terms of slope, how steep it is. The formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So this time we're going to take these two, and so I'm taking y sub 2, which is 8, minus y sub 1, which is 5, so that's 8 minus 5, over x sub 2 minus x sub 1, which is 6 minus 4. And so the slope is going to be 3 over 2, or 3 halves. And so this is what we call the slope of the line joining those 2 points. Okay? And again, maybe a little bit tighter bringing it in, if you could, John. Still keeping the edge here, but I want to just focus on, okay, that helps for people trying to see this. 3 different formulas. One is in slope, one is on midpoint, and one is in distance. And you really need to study how those look different. Because what frustrates me is on exams when I ask students to give me a formula for distance and they give me a formula for slope, or if I ask for a slope, they give me midpoint, it's not good. You need to know the difference between those. 3 different formulas. Now that's part of what we're doing there. Let's come back to the document cam for a moment. And that is, again, the midpoint formula that we have there, and then I'll want to come back center with camera 1 on me when we come from there in just a moment. But notice it's x1, and I say x sub 1. Technically I should be saying x sub 1 plus x sub 2. That would make it a little bit easier. So anytime you're ready to come back, center. Okay, and again, bring that in tighter if you could, John, please. Now, I'm going to go beyond there to what we talk about as graphing a line. Okay? So we're going to look at equations. And there are going to be 2 equations that I reference. One of these is on page 672. Okay? So on 672, we can go to the document cam. I have 2x plus y equals 5. Now that's an equation. It is 2-variable equation, or it is a 2-variable equation. I have an x and I have a y, and note that the exponent on the x and the y are both understood to be 1s. So that's 2x to the first plus y to the first. So we refer to this as a linear equation. Now if the exponents on the x and the y were 2s, we call it a quadratic equation. And so what is the difference between a quadratic and a linear? Well, a linear is going to give us a line when we graph it. A quadratic equation is going to give us either a circle, an ellipse, okay, a parabola, or something called a hyperbola. Those are called conic sections. Now I want you to note on example 6 on page 673, as we cut to the document cam, I have y equals 1/3 x minus 5. Now let me tell John where I'm going next so he knows where to bring cameras. I'm going to go to the sideboard, so camera 2 over in that empty space. Bring that around now because I'll go there momentarily and I'll be on the document cam when we make that change. So we have 1/3 x minus 5 on the right side. What I want you to recognize as we look at this equation, this coefficient, I'm on page 673. This has y by itself. Now, this form that you're seeing here is actually going to be given a name, and it's going to be called the slope-intercept form. And John, I'll want the far left side of the board, far left side when we go there, not yet, but bring back to me and then just bring the camera to the far left side of that side board. As we come back to the document cam, back to the document cam, this is where the line crosses the vertical axis, this minus 5, and that 1/3 you find in front of the x is called the slope. So we know this line is going to meet the vertical axis at minus 5 and have a slope of 1/3. Now all we are going to do, as we come off there, is we're going to plot points and join the points. All we need is 2 points. But I want you to be aware that there are easier ways of doing it than just plotting points. If we know the slope and we know where the line crosses a vertical axis, we can plot it even faster. Now, there are 2 other special lines I want to talk about before I go to the side board. And one is a horizontal line and the other is a vertical line. And they're shown very nicely in your text. As I come down to example 7, page 673, we have y equals 3. Now that says no matter what x is, y is going to be 3. So the graph that I draw, I'll just slide this down while we have it there, is that horizontal line going through the vertical axis at 3. So this is the line y equals 3. Now notice, no matter how much I change x, y doesn't change. So we say the slope of this line is 0. A flat line, a 0. If we had it at an angle, then there would be a slope more than 0. Okay, coming off there for a moment, I'm going to go to yet one more example called a vertical line. And this is what we see here, in which the line is going through the x-axis at 2. Okay, so this is a vertical line. X by itself will be vertical. Y by itself will be horizontal. And by the way, this line has an undefined slope. Otherwise, the difference between any two x's is 0. And so that slope we have, which was x sub 2 minus x sub 1 in the denominator, that gave us a denominator of 0, and we can't have that. I talked about the y-intercept. I'm on 674. So we go back to the book. There's an x-intercept and a y-intercept. All it means is where the line meets the axis. So what I'm going to do is just bring this down gently. There is a line, and notice that line crosses the vertical axis down here. So we say its y-intercept is minus 2. It crosses the x-axis at a 4. So the x-intercept is at 4. Notice the ordered pairs. For the x-intercept, 4, 0. For the y-intercept, x is 0, and you get the negative 2. If I can get those two intercepts, I can get my line. So we have several different ways of graphing. And what I'm going to do is look for the moment at another equation. So let's come off there for just a moment. I'm going to come up with this equation, and that's on page 675. Let's bring that to the camera. So that's the equation I'm going to look at, and I'm going to do it in different ways. So let me take some chalk with me. I'm going to go over to the sideboard, and what we'll do, let me get over there for a moment, John. Let's leave that on the screen for a moment. And I want about the same kind of shot that we had up front on the side. Okay, so drawing my coordinate system as we go to the sideboard whenever you're ready. Bring that in tighter again, just a little bit. Now, I need to label this, and so that's where I want very nice uniform labels. I expect to use a straight edge. Okay, and so I do that coming down and across, same scale all the way across. And I may or may not choose to put numbers in here consistently, but 1, 2, and 3. Here's a negative 1, a negative 3, a 1, 2, and 3 coming up here, a 4. This would be negative 3 over here and negative 2. I don't want to get this looking too cluttered. Let's go back to the document cam for a moment. I have this equation, which is 3x minus 4y equals 12. Now to the board. How do you find points that satisfy this equation? That's the difficulty. Now, the simplest way of graphing, and this to me is probably the method I use more often than any other as long as the numbers are nice. I try to avoid fractions. But I ask, what happens if x is 0? So I want this ordered pair. Now remember, if x is 0, wherever the line hits the vertical axis is called the y-intercept. So just let x equal 0. I cover up the x, and I have negative 4y equals 12. Can you do that in your head? If negative 4y equals 12, is it clear that y is negative 3? If so, I have an ordered pair right down here. That is the y-intercept. It's that easy. Okay? Now remember, on the x-intercept, y is 0. So I'll just make another ordered pair, but I'll put a 0 for y. So I'm going to cover up the y term, and 3x equals 12, so what does that make x? Does it make 4? Can you do that in your head? Okay, so I have a 4, 0. So I go out one more spot here, and here's my other ordered pair. I have two ordered pairs. Therefore, I have a line. Now, we've talked about a line segment as opposed to a line. So to indicate to you that I have a line and not a line segment, I'm going to go past those points. I'm going to put little arrowheads on the line to indicate it's going forever. That's it. Two-intercept form of graphing. Two-intercept form. Now, as I've said to you, I'm becoming much more much more conscious of the fact that I'm doing columns here using a BlackBerry. Two-intercept form. That's the technique I'm using. Two-intercept form. Let me just step off camera so you can just see that. Okay, a question. Marisol. Okay, at the moment this is the two-intercept form. Now I'm going to do two other techniques here in a moment. I'm going to solve this for y. Now right now I have it in what's called standard form. So this is a standard form. And if I have it in standard form, getting intercepts is pretty nice unless I have something silly like say a 13 here. Instead of 12, if I have 13, then I'm working with fractions, right? And that's not so nice. So the two-intercept form is not the only game in town. But I am going to solve this. Now we're going to move to the right a little bit. And so I'm going to have negative 4y. I'm going to isolate the term with y by itself. And the 3x I subtract from both sides, so I get negative 3x plus 12. I'm going to divide both sides by negative 4. And I generate this equation. 3/4 x minus 3. Now what I mentioned to you is that this all by itself as a number is the intercept. It's again the y-intercept. So that tells me this is an ordered pair I have. And indeed, that was an ordered pair I had in my graph. This part right here is going to be the slope. Okay, and it's telling me that the change in y, sometimes called the rise, over the change in x, sometimes called the run, is equal to 3/4. Okay? So let me just keep moving over here to the right just a little bit and let justify here for me, John. I'm just going to redo a quick sketch of the graph because it's going to be the same graph, but we're going to look at it from a different perspective. Here is 0 minus 3. Remember, that was my intercept. We did that before just by letting x equal 0. Now, what I'm going to do, rotate my hand so I can get those the same distance. Now, remember the slope is 3/4. That was the change in x. So if I run x over 4, so there's 1, 2, 3, 4, then it says y is supposed to go up what? 3, which puts me right. Okay, so if again, 1, 2, 3, this is coincidental in this case, but here is my change of 4, 1, 2, 3, 4. So I made a change here of 4. That was my run. And when I did that run of 4, I went 3 up in the process, and that gives me the other point. So it was over 4 up 3. That's what it means to have a rise of 3 over a run of 4. And so I started with this intercept, get a second point, and join the line, or the 2 points from my line. Same graph, different approach. And before I answer your question, let me tell you that this is called the slope-intercept form. And that's one that we use in our courses, whether it be beginning algebra, intermediate algebra, statistics. That becomes a very important form, and its general form is y equals mx plus b. And m is used for the word slope. Okay, Michael, question.
Well, the run's always going to be a horizontal?
Yes, the run's always the change in x. So this run was what we called x sub 2 minus x sub 1. And the rise is y sub 2 minus y sub 1. Okay, and you may, in terms of construction, heard of runners and risers on building stairs. Well, the riser is how much you change in the vertical, and the runner is how much space you have on the step before you step upward. And the slope of a staircase. This is just like, here's where you put your foot, and then you go to the next one up here, and you go to the next one up here, and walk upstairs. And the steeper those steps are, the harder it is to go up. Okay? Now, there's a third technique, and it's just hunting for ordered pairs that are nice ordered pairs. And I say nice in the sense they work well, and they're sometimes hard to see. So let's move over to the right, same equation. I'm back to the form 3x minus 4y equals 12. Now, in this form, we oftentimes get what we call, I'm going to do it in this way, get a table of ordered pairs. So we make what looks like a T. I call this x, and I call this y. And the idea is to pick any x you want and solve for y. Now, if you choose wisely, this works out pretty well. If you choose badly, you can get a bunch of very poor-looking fractions. And I like fractions, but this is not where you want fractions if you can avoid it. Trying to graph 1 2/7 sucks. No way of cutting it. Graphing a 2 works. 1 2/7, you're guessing like crazy. So what would I like for an x that's going to give me a nice y? Well, see what we can do there. It's not looking too profitable here. If I get an x here and I subtract it from here, and then I want to divide it by 4 and have a nice number when I'm done, I could let x, for example, let me see what I can do here. If I run, I'm trying to run different numbers in my head here for values of x. 7, don't like that bad number. 6, 18, 30, not great, but I can try it. I'm going to let x be negative 6, just for the heck of it. Now, this isn't the best result in the world, but it'll work. That's going to give me a negative 18 here, correct? 6, or 3 times negative 6, that'd be a negative 18. So I'd add 18 to both sides, and I would have negative 4y is equal to 30. So y is going to equal negative 30 over 4. And that's not the greatest in the world, but it's negative 7.5. Do we agree? Now, halves I don't have too much trouble doing, but you can see it's not as easy to get a nice-looking ordered pair. Nice ordered pairs are integers. Not so good ordered pairs have fractions in them. And really sloppy ordered pairs have fractions that aren't like a half. Okay, let's try another one, see if I can do any better and get something that's going to work there. Let's try. If I go ahead and do a negative 8, let's see if I can get a better result. What are you going to have now if I have negative 8? Okay, this is going to be negative 24 here, right? So negative 4y, I add 24 to both sides and get a 36. And so y is very nicely a negative 9. I like that. That's a good ordered pair. So we're going to classify ordered pairs like we do behavior of kids at Christmas time. Have you been naughty or nice? Is this a naughty ordered pair or a nice ordered pair? This one's nice, that's not, hence naughty. Okay, can you find me another number that works as well as that negative 8 did? And this is a lot of mental gymnastics to carry this through this way. This is why it's not one of the preferred methods. Can you find me another ordered pair that would be nice to graph? Negative 12 what? For x at negative 12. Okay, if I do negative 12, that's going to give me a negative 36, so that's going to be a 48. And 48 divided by 4 is 12, and I agree. So negative 12, 12. Not bad. Okay, Kim. Well, let's substitute the negative 12 in for x. So that meant I had 3 times negative 12 minus 4y is equal to 12. Okay? So what am I going to do? This is negative 36 minus 4y equals 12. Now I want y by itself, so what do? I add 36 to both sides. So without showing that, do you see where I'm getting 48? Yeah. And now I divide both sides, and I don't like the way that 8 looks. So I divide both sides by 4, negative 4 to be technical, and I get y equals negative 12, which is what, just a minute, should I have had a negative 12 there? Ah, that's an error on my part, correct? So that should have been a negative 12? Do we agree? So negative 12, negative 12. These are not easy to do. And furthermore, where am I going to have to be to plot those 2 points? I'm not going to be here and here. Okay, if I'm at negative 8, I've got to be out, way out. And then I've got to be out to negative 12. I don't even know if I can get out that far with that graph. But when I plot those points, they'll be on that same line. So this is my least favorite method. My favorite method, to-intercept or slope-intercept. Tabitha. For an x, you mean instead of these nice negative 6, negative 8, you didn't like those bigger numbers. So what Tabitha's asking, could I have done something like a 2? Okay, let's see what happens if you run a 2. 3 times 2 is 6. So I'll subtract 6 from both sides. So negative 4y is equal to 6. So now y is negative 3/2. Not bad. But I wanted nice integers. Nice integers. Okay, so let's see if I can get a large enough x to make this happen. So what I would like to do is get an x big enough so that when I get an answer, it's a multiple of 4. So let's try something like x at positive 12. Okay, so I'm going to let x be positive 12, not negative 12. So I have 3 times a positive 12 minus 4y is equal to 12. So that means what? What am I going to have for that? It's too crowded. I don't like that. Let me give me more space. Still have room there. 3 times 12. And I have negative 4y is equal to 12. Okay, so this is going to be what here? This is going to be a 36, right? Which I subtract from both sides, and I'm going to get a negative 24. So negative 4y is equal to negative 24. So y is equal to what? 6. So if x is 12, y is 6. You like that better? Still not small enough, is it? I'm just going further out this way, up, sort of like Buzz Lightyears to infinity and beyond. I can do infinitely many choices. There is no ordered pair that I can't get. I'll rephrase that. Every point in this line has an ordered pair. I just have to find it. And there are infinitely many, so we can do this forever, always getting new points. What Tabitha is wanting are some nice small numbers. But when you try these nice small numbers for x, you get a bunch of fractions that aren't so nice to graph. So, it's a wash. You trade off big numbers for nice ordered pairs. We got it? Question, Bulmaro. Where would I plot the negative 7/2? Okay, let's slide over a little bit more, John. You have to sort of watch the zoom on this again. Keep it in tight. Okay, here's x and y. Now, to do this, I need to pull this in tighter because it's going to get really lost if we don't. And up a little bit more. Okay, I'm going to do this 2, 4, 6, 8, 10. So I'm counting by twos. So 2, 4, 6, 8, and 10. And then doing that, I have 2, 4, 6, 8, and 10. So 2, 4, 6, 8, and 10. So if I had a 12, 6, I'm going to have to go out a little bit further. And so this is, the point being here, you very quickly do what? Create problems for yourself in terms of your scaling because you've got to go out so far. This is at 12 now. So I am going, we said, over 12 up 6. So here's my up 6. I think that looks about level. So here's over 12 up 6. And here's an ordered pair 12, 6. I'm still doing the same line. Yeah. Now, negative 6, so let's take another ordered pair, which is the one Bomaro was asking about. There's negative 6 at this point, and I want to be down what? Negative 7.5. So I have this for my distance. That's 2, 4, 6, 8. So this is at negative 6, negative 8. Here's negative 7. There's negative 7.5. And now, same line. Unfortunately, you can see it crosses where? At 4, 0. We can pull out just a little bit now, John. Just a little. There. And this should be at what? If I've done it carefully, this was 2, this was 4, and I didn't quite make it where? It was supposed to be at 0, minus 3, and so I didn't quite keep my scale uniform. Again, I don't care what points you choose. If you do them carefully, you're going to get the same line. Pardon? Well, if you didn't get the same line, then you've been very sloppy, or you've made a bad choice of an ordered pair that didn't really satisfy it. See, what I want you to realize, and let's slide over now, John, to here, just to this point. I guess I should be using a more technical term called panning, but sliding and panning. These ordered pairs are all on the line. They are the solutions of this equation in two variables. Tweak just a bit to get that. Thank you. Again, every ordered pair I have here is a solution to that linear equation in two variables. So how many solutions do I have to this kind of equation? Infinitely many. Okay? Infinitely many solutions. And so when I graph the line, I'm graphing the solution set for this linear equation in two variables. There is no way that I can give a single ordered pair. Now what's interesting, yet to come, this is a preview of coming attractions in another lifetime called beginning algebra. You can have a system of two equations, two variables, two lines, and they can meet at one point. That's called a system of equations. And there will be just one point shared by them where the lines meet. Okay? Okay, it's an intersection point. It's called the simultaneous solution of a system of linear equations. So as we slide over, John, a little bit more, panning to the right, I'm going to have to stop here pretty soon because I'm running out of room. But again, I have a coordinate system. And let's just say I had a line like this. This is L1, L sub 1. And let's say I have a line like this and call it L sub 2. Then this is the xy that is in favor of both lines. That is, it is a solution for both lines. There's only going to be one such point, and we find that by graphing. That's one technique. So this point that is shared is called the simultaneous solution for a system of linear equations in two variables. We didn't say that always the language was so elegant, but I have a simultaneous solution for a system of linear equations in two variables. And I can do that by graphing. And there are about 3 other methods I can use, which is what's being done in the Math 70 as we're finishing up the semester. That's one of the things that's being done there. Okay, so what I want you to do at this point, John, would you go back to the document cam, please? Now that all started with that little simple equation. And I've covered a bunch. Okay? As we come back center, bring it in tighter, please. Now, in terms of what we've done, we have done a kind of solution, if you will. We've done a solution for a slope-intercept. We've done a solution for a 2-intercept. We've done a solution for pick your poison, meaning pick the ordered pairs. That's not so easy. Thank you, Debbie. And what we've done is look at plotting points, graphing lines, and I don't know how much trouble you're going to have with this. I mentioned to you when we did this with simple closed curves. With simple closed curves, we had no problem plotting points. But I know what happens between that and a beginning algebra or intermediate algebra or a stat course. It wasn't something you got frustrated over, and so you forgot it very quickly. I'm coming to the conclusion that if it's not frustration, you may not remember. So when I talked to Sarah about what she did with this, because she's a couple sections ahead, she didn't do 8-6. And she said when she went through this, her students really got a little bit choked up about graphing lines. And she didn't mean it choked up in a polite way. They choked in terms of doing it. Now, I've gone further than what she did with the premise that if I challenge you a little bit more than what's here, I'll get you frustrated enough that you may remember what I want you to remember. So I'm sort of going on this basis, a little bit of anxiety is worth maybe doing. Now, I'm going to make a restriction on you. When you graph lines, you do not use graph paper. When you graph lines, you do not use these nice little diagrams in your book like this. Every time you do this, I want you to draw the coordinate system and label it. Reason? If you don't draw coordinate systems, it doesn't work as well. If I just hand you graph paper, you don't get as much out of it. So you draw a coordinate system for each one, and you have, starting with number 23, going through number 42, in fact, going up through 48. So 23 through 48 is about 25 problems of graphing. I'd like you to do them all on paper for tomorrow. Your choice of what technique you want to use. 25 problems that you graph the line. Michael, you're first.
Can we draw our own graph paper?
No, I want you to draw a coordinate system like I did and draw a new axis each time. Now, you aren't going to make a coordinates. No, you're not going to format one and then duplicate it. You're going to, each time, Draw me a coordinate system. Okay, Robert. 23 through 48, all those that you're graphing, starting with number 23. So that gives you about 26 problems, I guess. I want them ready to hand in tomorrow. Ready to hand in tomorrow. I don't want you on the computer tonight. I want you off the computer. I want you on the paper. I want you using a straight edge. I want you drawing lines, giving me ordered pairs, giving me coordinate systems. I want 2 to 3 hours from you tonight if necessary. I think it stops at 48, or did it go beyond there? Well, if it goes to 50, why not? Up through 50. The more the merrier. You just start in 23 and go to the end. You're on section 9.3. So I'm hoping that you've been challenged this morning. That's my intent. I took you beyond where this book is, with intent. If I have some frustration for you today, I'm happy about it. And if you really grind this out 2 or 3 hours tonight, I'll be very happy about it. And when you come in tomorrow, you have everything ready to show for what you've done. Nice, neat graphs. Okay, and we will critique them tomorrow with a Q&A. So Debbie, I've run out of time.